Thank you all for joining us. We want to thank you all for attending and making this such a great conference, and especially to all of our panelists. You're what makes this all possible. Just as a reminder, please avoid any ex parte matters or matters pending before the commission, though I don't think we've had any problems with that on the prior days, and I'm not expecting it this session. If any of you need coffee, there is a snack bar on the third floor. I know we've been pushing pretty hard these past 2 days, but the end is in sight, and we are in the commission meeting room only for the next session. This is the last session in hearing room 1. All right. So starting us off today is Alexandre Parisot with his presentation, Embracing Open Source and OSS Projects to Improve Energy Market Efficiency and Reliability. Alexandre, take it away.
So, good morning, everyone, and thank you very much for FERC and its staff for organizing this great conference. So I'm Alexandre Parisot. I work at the Linux Foundation. Linux Foundation is a neutral hub, a nonprofit where we help organizations and software developers initiate, manage, and scale open source projects. So starting with Linux, so large industrial open source project, but branching out into many other industries. And so let's see what it can do for the energy industry. So next slide, please. And the next slide. So let's start with discussing what open source is, understand what it really is. At its core, open source is software, hardware, data, and standards that anyone can view, change, share according to a permissive license. So the license sets the rules, but then you can do a lot of things. And one of the things that you can do, especially with open source software, is if there is something that you don't like about the software, you can go to the source code and you can change it to be exactly what you want it to be. And if you actually share that back, others can actually view your changes and determine that it's actually something great and improve upon them and maintain them on the long run. And it creates this kind of collaborative environment. So really open source enables a way to collaborate on R&D. It allows you to do a lot of things like avoiding duplication of effort. If you've got like peers or competitors, so usually they have similar needs. So instead of doing 3 separate projects, they can share what is common and share the effort, the development, and the maintenance cost, and they can still actually differentiate or do something specific, or actually even compete on the things that are actually specific or where they have particular skills or IP. So it allows them to actually share this. It ends up having other benefits, like for example, we see that open source usually ends up with better code quality. Why is that? For a very simple reason. If you do an open source project, you want to welcome contributions. You want others to actually contribute. Others will contribute if your code is actually readable, well documented, well organized, and basically others contributors will be encouraged to actually do the same thing. So we see that actually it ends up raising the code quality, and that's one of the reasons why usually actually software developers themselves, they love working on open source project, because there is an encouragement and incentive for this across the board. It's good software development. It helps also with interoperability. Usually when you want to make interoperability, you actually have to agree on a common specification, on a standard, and then everybody goes and in good faith implements whatever is in the document. But usually there's room for interpretation. If you go open source and you do this in the same way, you directly work on the interoperable piece of software. So basically you construct it together, and everything is actually explicit. It's actually written in the code itself. So there's no more room for actually interpretation, and you get actually the software as it goes. You don't have to wait for the specification to be final to actually implement it. So there's a lot of benefits like this. Next slide, please. So one of the things one of the questions that I hear actually from you a lot of the time is, how is open source compatible with actually making money, business? Well, it turns out that there's many ways you can leverage open source as part of a sound business strategy. And one of the ways you can do this, you start with the open source project, And you use that to actually make a product or service that actually leverage this. And that product, that service you can sell, you generate revenue, and you can make that into profit and actually feed that back. You create that kind of reinforcing loop, and that is a way to actually make open source into a sustainable initiative. You can sustain this from a business point of view, and that's usually where we find that's one of the actual recipe to make really large scale open source project and scale them in this. And if you look, for example, at some of the most valued IT software companies, you'll find that they're actually also the ones that contribute to open source the most. So there's no incompatibility between open source and actually making money. Sometimes actually it's rather helpful in fact. So next slide, please. Another thing that we tend to hear very often is, well, open source may not be secured. Why? Because, I mean, what people think is that anybody can look at the code, so anybody can find vulnerabilities. Well, it turns out, yeah, that's true, but that's also true for all the other people that are also involved in actually making it happen, collaborate on it, and sometimes have business interest in there. So you've got a lot of eyes actually looking at the code and trying to actually look for this vulnerability with the goal of actually patching them. It also works for bug fixes. So, and if you can also automate this kind of thing. So there's a lot of good best practices that you can share around this, which are actually part of this open SSF Foundation. And so usually open source can actually be made secure to the really highest standards of cybersecurity. And if you actually don't believe me, the Department of Defense has actually said that open source is its preferred way of procuring software. So that means that, I mean, you get to the highest standards in there. Next slide, please. And so, well, one of the last general point, is that kind of open source, magic? Can it actually works in an industry that's pretty old, pretty hardware intensive, heavily regulated, that essentially is present in everybody's, everyday life and supports an entire economy? Well, look at telecom. The telecom industry over the last couple of years has actually started embracing open source with its major actors. And what they've seen is that it's completely increased the pace of innovation. It actually lowered cost and it transformed the entire industry and made a lot of the things that now the telecom industry is already benefiting from it, including, for example, 5G deployment that occurred, rather much faster through open source. So it can happen in an industry that shares a lot of features with the energy industry. So let's go towards the energy industry now, more specifically. So next slide, please. So do we have open source in energy? Well, we did a little bit of a landscape exercise and tried to find out what are the open source projects in energy. Well, it turns out there are a lot, so there's a lot of initiative, there's a lot of people interested in doing this. Do all these projects actually have all the characteristics that I actually mentioned before that makes into this large-scale collaborative effort? Not necessarily. It actually takes a lot. Next slide, please. So at the Linux Foundation, we actually focus on getting all the environment, all the necessary ingredients for this project to actually scale and get all these things. That goes from, going into, the right governance, the right maintenance, the right cybersecurity practices, the right license. You have to choose a license that actually is compatible with your business model, but also welcomes other people contribution. You have to have all these things in order to get all the benefits and all the collaborative environment that I spoke before. So next slide, please. So at At the foundation, we're actually starting about 5 years ago, focusing on how we can help the energy sectors and its actors do this kind of projects. And it ended up right now having about more than 30 projects that we're now helping grow and actually mature along this line. Some of them are not necessarily completely aligned with the scope of this particular conference, but actually 3 of them were featured in talks yesterday, where we had a discussion about trolley and the exchange of AR information in the context of FERC Order 881. We had possible, and our Artelis is actually using it in terms of possible metrics to do studies and other things. And we had the carbon data specification consortium. So I invite you to have a look at this particular talk sessions to actually learn more about this project. In the next 2 slides, I'm going to give you a little bit some more examples of other projects here that we have. So, for example, we have the Operator Fabric project. So, Operator Fabric is a platform for alert management for system operators. It allows to actually do processes for actual coordination between operators. This is actually one of the root of this project is the 2006 event in Europe, where the synchronous area was split in 3 zones, and one of the reasons was lack of coordination between operator. Operator Fabric is meant to actually address this critical aspect, and it's actually right now it's an open source tool, but it's actually deployed in every TSO to handle the exact same kind of critical processes that were at the root of this particular event. So this is an example of an open source project in this situation that can do a lot, and it's actually in production. So next slide, please. Another tool that I can mention is the Dynamo tool. So a Dynamo tool is a suite. It's a suite of simulation tools for power system. Its roots were actually lots of its roots were actually two R&D projects supported by the European Commission, Pegas and iTesla. And what it aims to do is a complete and coherent suite covering everything from power flow to short circuits to short-term and long-term stability and going into quasi-EMT. It has some principles like the separation between the modeling part and the solver. What it means is basically you do most of the modeling in Modelica, so actually write the equation, you actually write how the different devices can work, and actually the solver is completely separate, and the solver use the solver depending on the kind of phenomena that you actually want to study. And this tool is actually under development by RTE, and RTE is already using it some of its aspects as its main production tool. So it's going to become the official production tools that they use. So that sets the actual standard for this kind of thing. And this is a tool where actually you can look at it, you can use it, but you can contribute it. You can contribute to it. You can improve upon it. It's actually an excellent start, and you see it's an actual production tool, so it's going to be validated and everything. So this is really a good place to start. Where if you're looking for a tool that actually does this kind of a study, you don't want to start from scratch, and you want to expand on something where you can see everything in a transparent manner. Next slide, please. And so the last tool that I will mention is OpenSteph. OpenSteph is a platform to do short-term modeling of loads. So it actually leverages machine learning and AI, and it handles all the data pipelines that you need to enable this kind of thing. So again, if you're into forecasting, this is something that you can look at and use it or expand upon it depending on your needs. Next slide, please. And so talking more generally about AI, actually, we've been looking at how we can help also AI innovation and R&D across the board. One of the issues that actually comes up on the very top of pretty much everybody's list is for AI, you need access to energy data. Now we know that that accessing energy data sometimes is complicated because of entirely legitimate privacy and critical infrastructure protection issues. So if you want a discussion on this, I referred you to this piece in Energy Law Journal that was published recently and that discussed this a little bit. At the foundation, we've been looking at ways we can actually help in that sense, promote innovation by helping people access to data. Well, they can't really access the real data, but why don't we actually try and produce realistic data? And so in this situation, for example, we have the Open Science project that was initiated by Center from Net Zero. That's a R&D center that's affiliated with Octopus Energy in the UK. And one of the things that they do, they have access to smart meter data across their entire territory. And so they've been asked, can we get a little bit of the access to this? It's very complicated, and privacy usually makes it completely impossible. But they can train AI to actually produce synthetic data, so realistic profiles of smart meter data that sort of look like the real thing. So they have the actual features that you want to see, but you can't attribute any of those profiles to an actual customer. So you can alleviate a lot of the privacy concerns while giving access to the content. There are other ways you can also promote open data sets. So RTE, for instance, has been pretty involved over the years on producing open data sets for optimal power flow simulation, so test case that everybody can use, and that usually are pretty large and have the right features. So a couple of days ago, actually, RTE decided that they would that they would agree to release 3 years of snapshots, 5-minute snapshots of the actual topology changes on the entire French grid. So that would be the position of every breakers that they do in operation. And the idea is they hope that this can actually help a lot of research and innovation on topology optimization or transmission switching based on their own particular experience. And so in that situation, you would have the data trying to supplement it with some also snapshots of generation and load. Of course, that the real data is actually confidential, but trying to work out something that would be realistic, so that could be used as a tool for research and as a benchmark for the community to compare results and actually work on. So there are ways in which we can work in the spirit of open innovation and open sharing in order to make those information accessible while still preserving the privacy and critical infrastructure protection constraints that will be there anyway.
3 minutes.
Okay, thanks. Next slide, please. Next slide. So in the last section, I'm going to be talking more specifically about open source, your open source strategy, how you can actually leverage this. So I'm going to go pretty fast here because this slide actually a lot of people, I mean, you're pretty much aware of the changes that our sector has. It needs digital transformation. We need software improvement, especially with GET. I hope I've convinced you that open source is a proven and efficient way to do software. So, and it follows that basically every one of you in this room should say, I should have at least a strategy on how I can best use this. So it's generally underutilized. It's probably the case that you're already using open source, but you don't necessarily know about it, or you're not leveraging this kind of the kind of collaborative advantage that I've been talking about. I hear sometimes actually that, the kind of thing that we're doing is pretty niche. There's a very small community, and so it's very, very hard to do a collaborative effort. Well, the community is actually here. It's in this conference, so it actually exists. We've got a community that can collaborate. on things. And so the other thing is, if you want to do open source, do it right. You know, try to use the best proven practices for this. So next slide, please. So at Linux Foundation Energy, we're here to help. We're here to help you strategize on this and set up project correctly, help with your open source strategy, with your open source strategy, and help you connect with peers that actually can share best practices or ideas on how to actually pursue it. And the next slide, please. So in that last slide, I will actually give you some ideas and pretty quickly about how you can use it depending on basically different categories of stakeholders. So let's start with regulators and funding agencies. If you're a regulator, usually you want to be technology agnostic. You don't necessarily want to take sides. Well, actually, open source is not a technology. It's a way to actually collaborate. So you can actually encourage this and encourage open standards, open source procurement because of all the benefits I'm saying, but also because of the transparency that comes with it. If you are a funding agencies and you are actually issuing your funding opportunity, open source can be a way to actually get impact and get to market. So if we switch to R&D institutions, which are often the recipient of those things, my advice would be structure your project from the very beginning to be this kind of open collaborative effort. Welcome other people's contribution during the projects. Open source is not the thing that you do on the last day of the project. You've produced this amazing piece of software and you're going to put it on a GitHub in the hope that somebody will actually pick it up. Most of the time, that doesn't fare very well. But if you start very early, you can get adoption. You can get early release. You can get other users to actually give you feedback. You can get them to actually contribute with you, even if they're not part of your research consortium. So of course, the funding opportunity and has to be compatible with this, but this is something good that you can do. If you're a system operator and utility, of course you can. If you're not doing software development yourself, you can advocate for interoperable solution. But if you're actually doing software, if you're actually doing software development yourself, you can use open source as a way to partner with your vendors and your peers to actually co-develop solutions and get all the benefits from it. And lastly, as a vendor, look at your software stack. So perhaps there are parts in which that may be dealing with, for example, data exchange or integration with other systems. You probably don't want to open source your core components. That may not be the foundation of a sound business strategy. But basically, there are a lot of outside things that usually may be also pain points for your customers, like data format or exchange. And this is where actually you can lay the foundation of something where you can collaborate with your competitors or with your customers and do a lot of good things. So thank you very much. I'm a little bit over, but yeah, I'll welcome your feedback on this particular piece of advice and slides.
Thank you for that presentation, Alexandre.
Thank you.
Any questions in the room?
Thank you. Russell Ulrich, Polaris. Alex, you and I have had discussions about this, and I know that I'm a little bit of a skeptic, but it's not because I don't believe open source is useful. And you identified that your goal is to convince us that we should use open source, but you also identified that there may be places that it's not appropriate. The challenge, I think, with the open source community is that most of the people I talk with are like religious zealots. They are true believers and everything is open source. And there's not a discussion around where does open source make sense and where it may make sense to apply to your organization and where may it not apply, and to come up with the framework for people to understand where that makes sense. And if you were to start your presentation with that sort of understanding, then it'd be much easier for folks to see, oh, okay, this is where it fits, and I don't want to be wasting my time over here, at least not yet. So get away from the true religion and get to the technical framework that we can actually make use of. And in your role, that would be great place to do it.
Yeah, and I say, I mean, I think I pretty much agree with this. I think that what we see is you can definitely do open source. You can advocate for open source everywhere, but that may not be the best way to actually make very large scale sustainable projects that on par with Linux, on par with things like your Kubernetes, PyTorch. This is completely compatible with business strategy, even sometimes with proprietary software. It has to make sense from a business point of view to make it sustainable. And so yeah, I think the discussion. What I really would like to have is for our community to have this honest discussion about open source, not a black and white kind of thing, but think. I mean, the main message is think about it strategically. Consider it, and there will be places where it makes a lot of sense, and it can actually be very helpful for either your business or for the changes that you're actually undergoing as an organization. So think about it strategically.
All right, thank you. Do we have any questions online? Any more questions in the room? All right, Alexander, thank you very much.
Thank you.
All right, our next presenter is Mahdi Mehrtash, presenting Global-TEP, a new global solver for transmission expansion planning with AC network model. All right, Mahdi, can you take us away, please?
Hello, everyone. I'm Mahdi Mehrtash. I'm a research faculty at Johns Hopkins University. And in this talk, I will talk about a new global solver that we developed. We call it Global-TEP, which is about power system expansion planning, considering AC power flow equations. Next slide. So first, I will give you a very brief overview of the US power system. And after that, I will talk about the importance of power system expansion planning problem. And then I will introduce the software that we developed, the Global-TEP. I will talk about some of the contribution that we had there. And after that, I will talk about the byproduct of the Global-TEP, which was a larger scale test system for the expansion planning problems. And then I will compare the results of the transmission expansion planning problem when we consider the AC power flow versus when we ignore the AC power flows. And finally, I will talk about the recent extensions of the Global-TEP solver. Next slide. So I think we all know that the US power system consists of three major interconnections: Eastern, Western, and ERCOT. And about 2/3 of the electricity generation in the United States is under the umbrella of the electricity markets. We have 7 different independent system operators and regional transmission organizations. Next slide. If we look at the prime source of generating electricity in the United States since 1950, we can see that after about year 2005, we have a change in the pattern. So the coal consumption decreased significantly, while the gas consumption increased. We also have the increase in renewable production. Next slide. If we only focus on the renewable production, we can see that we have almost the same level of hydroelectric since 2005, as well as the same level of geothermal and biomass. However, wind and solar generations are increasing significantly in the recent decade. Next slide. It's a good thing that we have these renewable resources for producing electricity, but we should not forget the role of transmission lines. So if we invest too much on these renewable energy resources, but ignore the fact that we need a lot of transmission capacity to transfer this renewable generation to the load centers, we will face some challenges. I brought you here one example of the state of Texas, the ERCOT, that a lot of onshore winds has been installed far from the load centers, and there is not enough transmission capacity to transfer this clean renewable generation to the load centers. So that's why we are seeing a lot of wind curtailment in the state of Texas. On the figure on the right, you can see that from January 2020 to January 2021, the amount of wind curtailment in ERCOT came double. Next slide. But the good news is that we noticed that we need this transmission investment as well. So recently there have been a lot of news and funding about improving the transmission system and expanding it. And we have also a lot of federal funding to doing so. For example, in infrastructure bill and also Inflation Reduction Acts, there are significant federal money for investing and renovating the power grid. Next slide. So with this overview about why we need these transmission lines and the good news about we have enough funding for doing that, I will want to introduce the power system expansion planning problem to you, which is a decision-making problem about determining the best transmission reinforcement and resource investment in an existing power system. There are several reasons to do the transmission expansion planning. For example, to support load growth, to remove transmission congestion, to support integration of the renewable energy resources, also to provide transmission access for all market participants, and finally, to support system reliability. There are several challenges for the power system expansion planning problem. I mentioned just 3 of them here. I know that there are more challenges related to policies and environment. But from the mathematical perspective, these 3 challenges are the most important one. The first one is the size of this problem. This is a large scale non-convex problem because we have the AC power flow equations in the model, which are nonlinear and non-convex. The second major challenge is the presence of uncertainties. Expanding the power system for the next decade requires long-term forecasting of the demand and renewable. And we know that long-term forecasting by nature has a lot of forecasting errors in itself. So that's why we should consider these uncertainties in the planning problems. The third challenge is about expanding a system that is physically connected but operated and owned by 2 different entities, and they are not willing to share their information with each other. So in this presentation, I mainly focus on the first challenge. I addressed the other 2 in my other publications. But here I would like to talk mostly about the scale and non-convexity of the transmission expansion planning problem. Next slide. Here is the publication that we had about this global survey that had been published a couple of years ago in Transactional Power System. Next. But first, let's take a look at what the AC transmission expansion problem is. So the objective function of this optimization problem has 2 main parts. The first one is about the investment cost of the new lines or resources. And the second part is a term representing the operation cost of the system. It could be total system loss or total generation cost. And we have a bunch of technical and economical constraints. For example, the budget limit, the thermal limit of transmission line, nodal voltage limitation, unit production limits, as well as 2 very important nodal power balances for active and reactive power. And last but not least, the AC power flow equation, which is the source of nonlinearity and non-convexity of the ACTP problem. Next. So if we want to see, okay, where this nonlinearity comes from, assume that we have a typical transmission line connected sending node I to the receiving node J. If we write the Kirchhoff's voltage and current laws and do the math, we will end up to these 2 equations I shown on the top of this slide for the active and reactive power sending from bus I to bus J. Here are shown variables in bold. So you can see that we have sine and cosine. We have a multiplication of 3 variables here. So it's highly nonlinear and non-convex. And from the optimization perspective, there is no way to convexify that exactly. And this is the situation for the existing transmission line. If we want to model a candidate transmission line, we should also add a binary decision variable shown here by XL, which makes the problem even more complicated by introducing integers into the problem. So in general, ACTP problem is a mixed integer, nonlinear, and non-convex problem. Next. But how to solve such a non-convex problem to the global optimality? So in most literature and in the past, it has been solved as a linearized approximation. So the linear approximation alternative of the transmission expansion problem is called DCTP. Here, as you can see, if we want to try to solve the DCTP, we actually end up to a result that is not even feasible for the ACTP problem. So in this figure, the objective values is on the y-axis, and the x-axis represents the variable domains. And this blue region is actually the non-convex feasibility region for the ACTP problem. So as you can see, the DC model solution is infeasible for that because it approximated the feasibility region of the ACTP problem. In some other literature, researchers try to solve the problem locally. So they may end up to this local solution shown in purple, which is a feasible solution, but it might not be the globally optimal solution. In more recent literature, researchers propose to first convexify the problem in a way that's shown here in green, and then find the minimum value. Again, this minimum value of the convex relaxation solution might not be feasible for the ACTP problem. So these local optimum and convex relaxation solutions, although they are not exactly equal to the global solution, they will give us important information. So a local solution is always an upper bound for a minimization problem, and the convex relaxation solution is always a lower bound of the minimization problem. So if we find a way to find a valid upper bound and a valid lower bound of the problem and propose an iterative algorithm to reduce the distance between these two, which is called the optimality gap, we can eventually converge to the globally optimal solution. And the first global solution for the ACTP has been proposed in 2019 by Dr. Qatar and Jab. As you can see, solving ACTP to global optimality is a very recent research direction. And here we propose the second one, which we call Global-TEP. Next slide. We had three main contributions in this Global-TEP. First, we proposed a feasibility-based bound tightening, which is an interval arithmetic-based procedure to reduce the range of the variables. Imagine that we have variable x between x1 and x2, variable y between y1 and y2. By performing interval arithmetics, we can find the bound of x plus y or x minus y or x times y. And we use this interval arithmetics to reduce the range of the variables before solving the optimization problem. Here in this figure, I showed some variables theta ij's that we had. They were initially between minus pi over 2 and pi over 2. But after performing FBBT, which just takes a few seconds, the range is reduced to these red bars. Next slide. But why this FBBT is very effective here in the ACTP problem? Because in power system, we have some features, right? So if you write the admittance matrix of a power system, there are some elements that are always positive, and there are some elements that are always negative. This is the physics of power system. And there are some elements that are much less than the others. For example, for transmission line, we know that the conductance is much less than the susceptance. And we also know that the active and reactive power should be within the thermal limit of the transmission line. And we have some desired values for the nodal voltages. If we use this information and do interval arithmetics for each of the variables, we can reduce the range of variables before start solving the optimization problem. And this is what we did here. Next slide. Our second contribution was to come up with a very tight convex relaxation for the ACTP problem. So we have a known convex relaxation of the AC power flow equation. It's called second order cone programming. And here we use that as well as adding a lot of relaxation tightening constraint to this convex relaxation to make it as tight as possible. So second order cone, if we substitute the score of the nodal voltages as well as these trilinear terms I'm writing here, VI, Vj cosine and VI, Vj sine, by UI, RL, and LL, we can write the ACOPF problem in its original form in a way that we aggregate all the nonlinearities and non-convexities in these three equations that I wrote in the middle. So if we delete the second and the third one and relax the first one by changing its equality sign to inequality, we will get the second order cone programming relaxation of the AC power flow equation. Next slide. But the second order cone programming relaxation is not good enough for our purpose because in our problem, this is ACTP, not ACOPF. We have integer decision variables. That's why we further tighten this relaxation by adding relaxation tightening constraint for the arctangent function, for the sine and cosine function, for the bilinear and trilinear terms. Unfortunately, due to time limitation, I cannot go to the detail of each of these relaxation tightening constraints, but here I just show you how it works for the arctangent function. So this red curve in the middle is the arctangent function that we relaxed. But by adding 2 underestimator planes and 2 overestimator planes, we can kind of reconstruct that in a way that the problem is still convex. So we delete the red curve in the middle, and we'll add 4 under and overestimator planes to reconstruct that in the model. Next. Our third contribution in the Global-TEP was about an optimization-based bound tightening technique, which is another bound tightening technique, this time by performing an optimization over the feasibility region of the relaxed problem. And this one was also very effective. So here in this figure on the right, I show the variables RL, which are originally between 0 to the value shown by these blue bars. And after performing OBBT, the range is reduced to these orange bars. So you can see that OBBT could be also very effective in reducing the variable ranges. Next slide. Here I would like to mention a very important feature of these kind of algorithms. So we know that the relaxation tightness of a convex relaxation depends on the variable ranges. And here we have both relaxation tightening constraint as well as bound tightening technique. So each time we reduce the range of a variable, we are improving the relaxation tightness as well. Next. And that's why the algorithm eventually converges. So here on the left, you can see the overall algorithm of the Global-TEP. And the code is available online on the GitHub repository. Feel free to take a look at that. And I see that there are some advantages in having open source tools. The equation, I refer you to the publication here for the equation of the Global-TEP. And after we proposed that in 2022 for the first time, we did some extension. Right now, the current version of the Global-TEP can co-optimize the generation expansion planning as well as reactive power expansion planning as well. Next slide. So here I want to show you some numerical study showing the performance of Global-TEP in compared to the state-of-the-art global solvers, SKIP and Cohen, as well as with the method proposed in reference 1 by Dr. Kadar and Jab. This is for the IEEE 24-bus system. As you can see, it clearly outperforms the other techniques. SKIP and Cohen, which are open source global solvers, they were unable to converge to even a feasible solution after long enough runtime because they do not have any information of a good convex relaxation like SOCP that we used here. And the method proposed in
Mahdi, you have 5 minutes.
The method proposed in one converged to the global solution, but it takes longer in compared to the Global-TEP. Next. This is for the same kind of comparison for the larger test systems for the 6-bus system and IEEE 118-bus system, and we can clearly see that Global-TEP outperforms the others. Next slide. Okay, after proposing Global-TEP, we noticed that there are not large-scale test systems for the ACTP problems, and thus we use this Global-TEP solver to come up with a large-scale test system for these studies. We have this case 1354 in the Math Power, which is a well-known case for the AC power flow studies. We use Global-TEP to come up with the candidate transmission line and generator units, and we benchmark the global solution results for that. In this publication at the bottom of this slide, you can find the details of that. And here also I want to talk about a counterintuitive observation that some of you might know, which is called Brace paradox, which is if we add a line to the system, a random line to the transmission system, it will actually make the operation of the system worse. So it's not that we can randomly add a line to the system and it will improve the operation. Sometimes it can make the operation worse, meaning that you might end up to a higher generation cost or higher power loss. Next slide. So this one, I think, is the most important slide in this presentation. That's I compared the solution of the ACTP problem when you solve it in a linearized form as a DCTP problem, when you solve it with the local solvers versus when you solve it globally. As you can see, if you solve it in a linearized form, here is this large-scale test system that we propose. It suggests installing no new lines. And this is the approach that most of the people will go with. If you solve it locally by some local solvers, we use Nitro here, which is, the most advanced local solver that we found. It will suggest installing 44 new lines in this large-scale test system. However, if we solve it globally by Global-TEP, it suggests only installing 6 new lines. And if we consider the possibility of investing in reactive power compensator, it will install only 5 new lines. And you can see how different the solution could be, depending on which model you will use. Next slide. And here is just the current extension that we are having for the Global-TEP. We are trying to consider the HVDC models as well as fax devices in this Global-TEP tool that we have to make it more usable and more realistic. Next slide. Yes, and this is the way that we are trying to further extend the modeling of the fax devices. We already have this static VAR compensator on the model, but for the series compensator, we are still working on the formulation and trying to add it to the Global-TEP model. Next slide. Thank you for your attention, and I'm ready if you have any questions.
Mahdi, thank you for that presentation. Do we have any questions in the room?
Alex Rudkevich, Newton Energy Group. So in your formulation, do you consider just a single snapshot for the operation of the transmission line and the generator?
Yes, in this example that I showed you, yes, that's the case. It's just the peak load snapshot of the system. But depending on how much global optimality do you need, you can add more operating conditions and more snapshots to the model. So for example, if you are not very careful about converging to a very small optimality gap, you can consider more number of snapshots. So we made the model in a way that it's a trade-off between runtime and the accuracy of the model.
And like one of the examples is like people talk about the storage as an alternative to transmission expansion. Mm-hmm. And you can't really evaluate storage looking at a single snapshot because of the chronology involved in its operation.
That's right. That's one of the things that we can think of is considering a storage model while we have more snapshots of the problem. That's great.
Do we have any questions online? Any more questions in the room?
Hi, thank you so much. Can you elaborate a little bit on the ability to parallelize this? You mentioned, is that only in the OBBT component?
That's right. So we know that, for example, in the lower bounding problem, we use CPLX to solve the lower bound problem, which is a mixed integer second order cone. And CPLX by itself can use parallel computing, right, if you have multiple nodes. But what we consider here as a parallel computing for the OBBT step is that because we have this OBBT, which are small optimization problems, and they can be run in parallel. So the number of OBBTs that we can run in parallel is twice the number of variables that we have in the system. So we have variables, we want to find their minimum or maximum. So 2 times the number of variables. And you can do this procedure in parallel, right? If you have like 100 nodes, you can assign each node to run one of these optimization problem and do this procedure in parallel. So for the parallelism, this is what we consider in the Global-TEP. But as I mentioned before, even in solving the lower bounding problem by CPLX or GROB, they can use parallel computing themselves as well.
Are there any more questions in the room? Going once, going twice, going 3 times. All right, Mahdi, thank you very much.
Thank you. Thank you.
All right, next up is Tamer Ibrahim, presenting on advanced reliability toolset. Tamer?
I'm not Tamer.
Oh.
I'm Ignat Vittel, I'm the second author.
Oh, all right.
He's
Ignat.
yeah.
Ignat will take it away then.
All right, thank you. So yeah, my name is Ignat Vittel. I coordinate the research that has been developed here by Tamer. Next slide, please. So what we're going to be talking about today is a little bit different. So this is focused on the process and procedure that goes into the annual transmission planning assessments that all bulk system entities have to complete. So this is part of the NERC TPL1 assessments that are required as part of mandatory compliance to ensure reliability, security, and stability of the system. So this is steady state and thermal contingency analysis of a given snapshot condition. This planning cycle is very burdensome at every planning entity. It requires lots of manual validation of contingency definitions, as well as the running and assessment of thousands or tens of thousands of individual transient stability simulation runs. As you begin to integrate more inverter-based technologies into the system, this increases the complexity and evaluation of the process. We use a topological simplification of the planning system when we complete this assessment. It is a bus branch representation of the system where the substation topology is collapsed into a single bus. Node breaker is the actual topology that is present at a substation. And it is required to look at the node breaker topology to understand how these contingencies are defined to get the correct protection sequence to allow for the clearing of the correct elements. We've developed a process where we can automatically map the node breaker topology directly from the EMS model into a planning case, use that node breaker topology then to automatically create and organize contingency definitions based on the NERC TPL categories, and then leverage computational capability to perform commercial simulations using PSSE, PSLF, TSAT, and then apply data analytic techniques to screen those contingencies to identify and prioritize contingency events that need to be assessed for further mitigation and pass to more detailed processes like protection and control definition. Next slide, please. So we have 3 modules within the ARTS toolset. So ARTS stands for the Advanced Reliability Toolset. And we have a node breaker module, which creates that node breaker definition. So the EMS case is the state estimation of the system through the energy monitoring system or management system. It is a real-time look at what is online in the system. It is a node breaker representation of the system. And one of the challenges with bringing that into the world of a bus branch planning model is that every time it takes a snapshot of the system, the bus numbers are rewritten. So there is no alignment between the EMS case and the planning case, which links the planning case bus numbers to the dynamic models that are required to run transient stability assessment. So it makes it very, very difficult to get an EMS node breaker case into a bus branch planning case. So we have a process now that uses topological mapping using graph theory to find edge vertices in the EMS case and automatically represent those in the bus branch model. And in a very, very short number of time. There's obviously going to be differences between a real-time EMS case and a forward-looking planning case. We log those differences and report them for validation. A 5-year out or a 10-year out planning case is going to have new lines, new generators, new loads that might not exist in the EMS case. Those are all captured and represented. Once we have those node breaker models in place, we generate all the contingencies. We can pass them to any commercial platform to run the steady state or transient stability assessment. Using the automatic contingency generation tool. Once those transient stability simulations are completed, we screen them using the contingency screening and ranking tool to identify voltage instability issues, transient instability issues, and inverter-based resource instability issues. Next slide, please. So when you look at the transmission planning pipeline, what does it entail? The traditional conventional planning process requires planners to spend several months looking at one-line diagrams from the EMS or from the drawing database and validating contingency definitions and ensuring alignment with TPL1. Those two processes take several months across multiple engineers at planning entities to complete. Processing the contingencies through steady state and dynamic analysis is, it is what it is based on the commercial limitations of the tools and the approaches that are used there. So PSSE, PSLF in high performance computing environments, you can create multiple instances and run those transient stability simulations pretty efficiently. On the back end, you create a massive amount of stability information. So we're monitoring multiple variables for every generator, rotor angle, power, reactive power, so on and so forth. We do this for all the buses in the system, study system as well. So there are thousands of variables that are monitored every quarter cycle at least. And we run these simulations out for 10 to 20 seconds during that process. So we create a fairly substantial set of results on the back end that need to be screened and post-processed to identify which are the new contingency events that create the most significant instability issues. TPL1 mandates that you develop corrective actions to mitigate those contingency events based on the severity of the violation. How do we update that process using the advanced reliability toolset? So now we build the node breaker process, node breaker models into the planning case. This is a process that is done in minutes now. We read the EMS XML readout and directly map it to the bus branch case. We define protection control groups based on the breaker topologies, and I'll go through an example of what that entails. And then once we have the protection control groups defined, we can generate the TPL contingency definitions. We've taken an Eastern interconnect model, and for the PJM footprint, we've generated 500,000 contingencies in approximately 10 minutes. So it is a very efficient process that is highly parallelizable. And once we have those contingency definitions, we run through the conventional contingency processing portion, which still takes the same amount of time. It's limited by the capabilities of the commercial platform that you're using. And then we again take those results and post-process them using a series of algorithms to identify how stability or instability is going to manifest in those simulations. Next slide, please. So this is just a visual diagram of where the data flow and data connections sit within the process. A user has to provide basically two inputs to this entire workflow, the EMS data and a single bus branch planning case. The automation then takes over to build the node breaker model, pass that into the contingency generation module, which generates the TPL contingencies. You can then use the existing dynamic data library to run and simulate those contingency events. That information is then passed directly in the relevant output file to the contingency screening module. So the commercial platforms use different representations of the output. We read those directly in as Python objects and evaluate them internally through the screening module. Next slide, please. Next slide. So one of the keys, as I mentioned, buses and between the EMS and planning cases are inconsistently labeled. Lines, transformers may have different impedances. There's a lot of differences that you have to be aware of when you're completing this process. It is a challenge of maintaining data consistency between what is represented in the model through the EMS and what we need to capture in the planning model. So we automatically map
You have
this.
10 minutes.
We automatically map this to the system and move on. Next slide, please. So what we're functionally able to do then is take that original planning case and map it into the commercial platform to the node breaker representation. And what you see is a rectangular around each of the bus bars that exist in the planning case now. If we go to the next slide. What that actually represents is a detailed substation topology underneath that bus bar. So in what you see in the orange is a full node breaker topology representation where those orange squares are breakers that sit internal to the substation. What you see in the orange is actually the one-line diagram from the EMS case. What you see in on the right is the planning case with node breaker represented in it. When you have a bus branch case, all of that information is collapsed into a single bus bar. Next slide, please. We map these topological differences as well. So what you see in the yellow circle are loads that do not exist in the planning case. We highlight them to show that sometimes there are inconsistencies, but those inconsistencies are recorded for planners to go back and validate the differences. Those inconsistencies can be trivial sometimes. It depends on how information is represented. So if you have auxiliary roads for a generator, they may not be present in the planning model. Well, they might be present in the EMS case, but the information is present for planners to go back and validate. Next slide, please. So what do we do when we have a fault, right? So why is the breaker important in this process? So when you have a fault with the lightning bolt on that line, depending on where that fault is, a signal is going to be sent to the breaker on one end or the other end of the line, depending on which zone it falls in to clear. So if it falls in zone 1 of circuit breaker 2, it will clear in the zone 1 clearing time of circuit breaker 2, which is default definition, and it'll capture that information. Next slide, please. What does this mean in practice? So if you look at the circuit on top, that is the bus branch representation of a circuit with a generator on bus 1 and 2 lines going to bus 2 and bus 3. If you look at the node breaker topology, the representation is much more complex. So to understand what a simple n-1 contingency might look like with a line fault on line 1 to 2, you actually need to understand where the breakers sit in the topology. So once you have an understanding of what this topology is going to look like, so if we look at circuit breaker 3, in the red box being the breaker that is the faulted breaker and actually has a failure to open as defined by a NERC TPL category, the contingency becomes a much more significant event where there is a sequence of events that result in both lines opening in a delayed clearing event. So a simple n-1 is actually a 2-element event that would create a significant transient stability impact versus just the n-1 event. Next slide, please. So we're able to automatically create all of these contingencies and pass the code to PSSE or TSAT to run those contingency definitions either as a translation to a bus branch contingency event or directly as a node breaker event. Next slide, please. We have the ability to customize and provide the default information that you might use in your protection process. We can assign different clearing times based on voltage levels across the system. We can actually represent relay models instead of default clearing times to run those contingency events. So knowing where the breakers are in the circuit allows us to accurately represent relays and protection directly into the planning model. So we're able to run analysis directly without defining clearing times in the simulation. Next slide. We also have the ability to represent some of the characteristic features that are needed to accurately capture modeling inefficiencies in the system. So we often need to include dummy zero impedance lines to make sure that you can clear a fault on the correct end of a line and run the simulation. Next slide, please. We can accurately capture more critical and severe contingency definitions. So this is a bus section fault where the fault is on the bus bar itself. When you look at that in node breaker, all of the breakers circled in red would be the breakers that need to open as part of that contingency definition, which again creates a much more significant contingency than simply opening a single element on the system. Next slide, please. Another category of contingency event is the breaker fault, where again a more complex definition is needed if you're looking at it in bus branch versus in node breaker. Next slide, please. So what do we do once we have all these contingency definitions? We need a way to efficiently post-process and rank the impacts that are going to occur across a system. We use a performance-based scoring algorithm that is able to look at critical characteristics of different waveforms, whether they be voltage, whether they be angle across the system, to prioritize and rank contingency events based on the severity of the impacts. So we look at these characteristics, pass them through a sigmoidal scoring and sigmoidal scoring function, and rank contingency events based on the stability impacts that are going to be observed in the system. Next slide, please. We can then go through these thousands or tens of thousands of contingencies that you've created and point engineers to the ones that create the most significant impacts. This is for voltage performance. We also look at it for transient stability as well as inverter-based transient instability, which are very different phenomena because conventional transient stability is based on rotor angle deviation and angular swing that may occur in the synchronous units in your system. There is no synchronous tie to rotor angle in inverter-based generation, and it manifests as a different type of instability. So we can look at both. Next slide, please. So that is everything that I have. I think what this process is aiming to do is looking forward at the pipeline of additional studies that are going to be required. Yesterday, I spoke about how the number of scenarios that individuals are going to have to address in the transmission planning space is going to increase exponentially. Introducing automation to that process is going to be critical to ensure that companies are able to process, evaluate, and determine the appropriate mitigations that are mandated by compliance requirements. Thank you.
Thank you very much. Are there any questions in the room?
So Polaris. So my understanding is that you're trying to generate the contingencies in a probabilistic way. So you're trying to.
There's no probabilistic way here.
Okay. So then when you gave the example of bus branch versus breaker node modeling and why it was important, you showed an example where, okay, this thing trips, and then what happens if this breaker fails? isn't that a probabilistic judgment at that point? Because you're kind of an N-1 kind of situation, or what would you?
No, so that is, it's not probabilistic because it's a contingency definition that's required by a standard to be evaluated. So the NERC TPL 1.5 mandates contingency definitions based on different failure categories that are critical to the reliability of the system. So you need to show that your system response from a transient stability perspective for a fault that would potentially occur on this is appropriate. Granted, it is a very rare fault, right? So the consideration of whether it's likely to occur or not is not taken into account in this process because it is mandated that you have to look at it.
So there's two use cases here. One where you have a contingency, a breaker trip or whatever, line fault. And then you can trace through, based on the protection system, what other things happened as part of that contingency. So that's one case. And that I can see very, very well fits into the structure you've defined. But then when you say you've got that picture, but then something else may happen, though you're saying that those other things that may happen are well defined by the standards so that you don't need to guess and say,
Yes.
We have to assume as part of that contingency that we're going to have a stuck breaker as one of the things that has to be dealt with.
The contingencies increase in severity. So a P1 is a normally cleared single element. A P2 is, faults internal to the breaker. A P3 is an N-1 or a G-1 -1. A P4 is a much more severe category contingency where it's a stuck breaker element. P5 is a failure of primary protection. So that example where you see it's on the bus bar where you lose the primary relay protection of your system. You have to evaluate that. P6 is N-1 -1, and P7 is failure of common mode contingencies. So elements that run on common right-of-ways that might occur at different voltage levels.
So the probability and impact of is already evaluated in the definition of those events. Okay, thank you.
All right, do we have any questions online? Any more questions in the room?
Alexandre Parisot, Linux Foundation Energy. My question is in light of the effort that's actually involved in representing the breakers for the studies, would it be possible to actually directly model do the planning studies with the detailed topology? That's why actually some of the TSOs ended up doing.
Yeah, so
it takes a lot of effort once, but once you do it, then
we write contingencies both ways, right? So we write them as a bus branch representation, but we can also easily write the contingency as open this breaker at this time, right? So we have the capability to do it both ways. The complexity comes in how the utility has updated their ability to run simulations in that particular platform, right? So there's issues with versioning that are still being sorted out in terms of the software. So PSSE 34, some entities use that. PSSE 35, some entities use that. If they haven't upgraded their dynamic model library to be run with PSSE 35, they're going back to run bus branch contingencies, right? So it's a slowly evolving process. One would hope you'd be able to get to node breaker and fully run it there because it's much more efficient and it lends itself toward automation capability in a way bus branch simply does not.
All right, any more questions? Anything online? All right, Ekna, thank you. All right, and finishing us off for this session is Aleksandr Rudkevich with utilizing locational marginal emission rates to achieve decarbonization goals. Aleksandr, take it away.
So the presentation should have been made by Emma Naden, and she's done the most of the heavy lifting on this project, but she couldn't make it, so I'm here instead of her. Next slide, please. We will, talk about the background, why we're doing what we're doing, and walk you through the study itself. So next slide, please. So the starting point for this particular project was that it's been commissioned by the Maryland Energy Administration to look at their decarbonization goals. And the study is still ongoing, so results are, whatever I presented today are preliminary. All the opinions and positions here are of those of consultants and should not be attributed to Maryland Energy Administration, and all the errors and emissions are entirely ours. Next slide, please. So the goal is, I'll get to that point. The concept that we will be using is the concept of marginal emission rate. And this is something that's been known for over a decade now and kind of looked at and forgotten and looked at again, but now attracts a lot of interest. And what it does, it effectively like analogous to LMP. So for any given location in your system on electrical grid, you would think like, if I increase the demand by a small amount, how would that affect the carbon emissions in the system globally? So that kind of analogous in that sense to the LMP, so that depending on how the system will respond, what generators will be redispatched in which direction, that would determine what the incremental emissions rates are going to be. So it's essentially very time and location specific, depending on the operation rules and transmission. As we argue that is a much better way to look at the carbon replacement than to use things like renewable energy credits, because it quantifies emissions rather than clean energy and directly addresses the problem. Problem is not with energy, the problem is with emissions. Next slide, please. To quantify the carbon footprint, we essentially attribute the impact of every element in the system on emissions using marginal emission rate. So for example, if we look at the load, at any point in time, you can identify the marginal emission rate for the load multiplied by the load, and that will be the impact of the load component. For the generator, it would be you take the difference between the generator own emission rate and the marginal emission rate and multiply it by the generation. So essentially, it looks at the difference, what it emits itself versus what it displaces. So if you have a renewable generator and you see at emission rate, marginal emission rate, what it displaces, depending on that, it makes a negative contribution to the overall system emission. Now, if it gets curtailed and displaces itself, then it makes no contribution to marginal emissions. No contribution to displacing emissions. For the transmission branch, you take the differential of the marginal emission rate and multiply it by the flow. So if you use that methodology, next slide, please, then there is a, So this methodology is now being adopted and looked at by a number of organizations particularly interested in achieving net zero kind of voluntarily. So and they're looking at alternatives to simply accounting for renewable energy because they recognize that not all renewable energy is equal. Next slide, please. So the methodology why we use it, that approach? Because there is a what is known as a carbon footprint theorem, which basically states that if we take the electrical grid at any point in time and take the contribution of every element to the to emissions and add it up, it will exactly add to the total emissions released by the grid at that point in time. That's the kind of essentially it provides you the exact accounting of how much emission were produced. The second important aspect is there is an optimality principle, because effectively what it does, it achieves pretty much what the carbon tax or a cap and trade system would achieve. Because how would it affect the investment in the renewable energy? It would basically focus on, so let's say you've got an amount of subsidy that you intend to spend on carbon reduction, you would direct that subsidy to the location and the technology that would give you the highest emission reduction per dollar of investment using marginal emission rate. So that's the second kind of optimality principle of that approach. So, and that gives you the tools to kind of, first of all, how you can look at a subsystem of your grid and identify its carbon footprint. That's the important aspect, because if that subsystem wants to decarbonize itself, then at least it has to be able to measure what its carbon footprint in the first place. And the second, it gives you the guiding rules on where to make an investment to do it the most efficient way. Next slide, please. So the case study is the study that was, and it's still ongoing for the Maryland Energy Administration, which is developing a pathway to 100% clean energy. So we're looking at how to decarbonize the electrical system of the state of Maryland by the year 2035. That's the goal. And the first question was, what does it even mean that the state of Maryland has decarbonized its electrical grid? So if the approach is we basically say, well, let's use the marginal emission rate and rely on carbon footprint theorem to do that. So first thing, step one, let's quantify what its carbon footprint is today, or actually in 2022 using the historical data, and then based on that, develop the pathway. Next slide, please. So we see it's a part of PJM, it's part of the electrical grid, and whenever you increase the demand in Maryland, it may affect the operation of generating elements everywhere in the system. Next slide. On its own, the state of Maryland is served by several zones, several companies within PJM, it's PG&E and PEPCA and Delmarva and APS. So we use historical data on how the different load zones contribute proportionally to serving the Maryland economy. Next slide, please. So the methodology, looking at the historical data, is we take the load by zone from PJM, that's known information. The second, what's very important, is that PJM, starting in 2021, began publishing marginal emission rate locationally with a 5-minute real-time resolution, with some caveats that for strange security reasons, cybersecurity reasons, they decided to publish only load nodes, but no generator nodes, which sort of makes very little sense, considering that if you have two nodes with the nearly identical LMPs, then you can expect that their marginal emission rates would be nearly identical. I mean, not instantaneously, but over a period of time, because the mathematics of formation, both indices exactly the same. It's a shift factor mathematics. So it was very easy for us to identify for every generator node in PJM what its historical marginal emission rates were. Now for hourly generation, we need to know what is net. So it's a combination of the SAMS data and published through S&P Global as well as FERC electronic quarterly reports, because the SAMS data doesn't give you production by renewable resources, but EQRs do. And finally, the emissions also reported by EPA, and therefore we get emissions by unit. So we were able to apply all this information and the formulas to effectively identify the 2022 carbon footprint of Maryland. Next step, next slide, please. So it's here it's presented what is done by individual company, and this data are in million short tons of CO2. And then I think the next slide would give it graphically, would be easier to see. Next slide, please. So we can see that so at the top, it's mostly the load that is responsible for the emissions, which sort of as expected. And the generation, it's a mix, because there is nuclear, which predominantly has a negative impact, and the thermal generation then has positive impact as well as renewables. But the net result, we know what is the footprint for what the footprint was for 2022. Next slide, please. So the study, how we do it, we identify the baseline results. So first we need to look at what happens if we do not achieve decarbonization in Maryland, and look overall at the whole PJM footprint. We run the analytics capacity expansion and economic dispatch modeling for in a long time. And then based on that, we identify the pathway. So what does it mean? Basically saying, okay, let's take what we identified as a base case and let's see what Maryland would do differently, which in this case, basically considered only one option, that Maryland can only operate within the state of Maryland. So it can only build inside the state of Maryland or retire inside the state of Maryland, right? So then essentially what they need to do, they need to achieve that combination of the new projects and retirement, so that by 2035, their carbon footprint, as we define it, would turn to zero. Next slide, please. So then essentially, this is simply an outline of the analytical framework we run using analytics model of PJM, run capacity expansion optimization, identify sort of factor in all the known policies in place by different states within PJM, identify direct prices and the new additions and retirements and all that goes in, and then run the production costing model in detail to identify marginal emission rates in the future years and compute the year-by-year carbon footprint of Maryland. That would give us essentially what is the benchmark over time that we need to reduce to achieve the zero footprint by 2035. Next slide, please. So the dynamics is shown here. As we see, in order to achieve the zero footprint, a lot more generation will have to be built in Maryland, and I'll explain why. So essentially, it's clear that instead of being an importer of energy, Maryland would have to become an exporter and build a lot of zero emission capacity to start exporting and displacing emissions outside of Maryland effectively and claiming that credit. Next slide. So the additions, however, turn out to be that We would love to build a lot more renewables. However, the potential is limited, and where, like, for example, for the offshore wind, where it can come online, this is predominantly in the Delmarva Peninsula, but that is a significantly transmission constrained system, and there is not much you can build because it's going to get curtailed, and the marginal emission rate in that location becomes very low. So you really don't displace much. So instead, in order to do that effectively, the only options that were available were to build nuclear. I mean, how realistic that is a different question, but that's kind of given the rules of the game, that's what we built. So next slide, please. So as we can see on the left, it's a composition of the energy supply for Maryland. Like on a monthly level, and we see there's a significant level of imported energy that goes into Maryland. And under the new conditions, first of all, we see it's nuclear is increased, that's the brown portion, and then Maryland becomes effectively an exporter of energy. And by doing so, it achieves the carbon neutrality. Next slide. So this simply demonstrates sort of how the composition is occurring under the base case and what happens in 2035 in the decarbonized case. So the first bar actually, it shows the 2022 level. As we can see in 2025, the load sees a little higher carbon footprint because of the demand growth. But at the same time, the negative part is also increasing because of the offshore wind development. And also, I believe there are some coal retirements planned for Maryland. So that's what ultimately we see. And as we can see, that verification of the production costing of the capacity expansion component demonstrates that we were able to achieve by 2035 under this strategy virtually zero emissions, zero carbon footprint. Next slide, please. Now this graph basically shows that marginal emission rates, this picture really provide a good guidance for the investment. So we see, like, for example, it's not really attractive to invest renewable energy in Delmarva because the MERs there are very low, and it's much better to do it sort of in PG&E or in PEPCO territory, depending, of course, or in APS, depending, of course, on what the technology is there and what the cost of that technology, because that also plays a role. Next slide, please. So in general, what we see is the first thing is it's really important to have this information because it provides the guidance. And we applaud that PJM started doing it despite all the sort of complaints that we have that they don't publish everything, but still, I think they made a major breakthrough in that. We know that New York ISO have been contemplating beginning that publications for years, like I think they call the Carbon Impact LBMP. So we really believe that it would serve the decarbonization process in the country significantly if every balancing authority would be required to provide this information. There are actually different companies that begin to publish this type of information, trying to use artificial intelligence. But in my view, the only credible source of that would be the company that really operates the grid and has the first-hand information on how the dispatch is formed. That would also help to kind of bring the decarbonization process in a better, I would say, metered, measured way and provide efficient signals to all the organizations that voluntarily want to decarbonize. Thank you.
Alexandr, thank you. Do we have any questions in the room?
Thank you, Vladimir Dworkin, University of Michigan. I'm not working with emissions, so maybe I'm a bit ignorant of carbon accounting, but the ideas of this locational marginal emission rates indeed resembles LMPs in electricity market. And one of the promise of locational marginal prices is that by looking at the differences in LMPs, and power flows, we can estimate congestion rent that will be accumulated by system operator. And if we play this game in the long run, we will eventually accumulate sufficient investments to invest in infrastructure and release congestion, right? And does the same intuition hold for locational marginal emissions? Can you gather some emission rent because of congestion in the network and then use it to then invest in, maybe in carbon storage?
Well, that's an interesting question, because technically, unlike congestion, that is always positive. The emission rent could be negative, could be positive, and depending on that, some congestion actually helps to reduce emissions, and other actually hurts, right? And so you can look at that, and that would kind of identify which. So, for example, I mean, speaking like if you have a trapped coal unit, you probably don't want to relieve that congestion, right? From that perspective. From many others, you might, but from that, you don't. But at the same time, if you have a trapped coal unit, you probably want to build a renewable energy next to it because it's on the margin and it provides the highest displacement. So essentially, it gives you the most efficient path to decarbonize. And until you until you do not curtail your renewable energy, you don't want to relieve that congestion. Once you begin, you see that, okay, now it's getting curtailed because of the coal operating predominantly at mean-gen level, then you want to relieve this congestion. So it's sort of like a dynamic game here in that sense.
All right, I think we have a question online.
Yes, we have one question online from Rajat Punjalia. I'm going to unmute you, Rajat, and you can ask your question.
Hi, can you hear me?
Yep.
Thanks. Hey, Alex, excellent presentation, very fascinating. I have a lot of questions. I'll try to be brief. Why do nuclear and renewables have negative net emissions? Shouldn't they be zero? And I'll just fire these set of questions and you can answer as you want. What does negative emissions really mean then? I'm looking at the equation as well. So if there are still CCs, ICGTs generating in 2035, how is the system carbon neutral? Who gives and what gives?
Okay, so I think it's not a negative emissions, it's a negative emission impact, because it's determined by the difference of what the generator's own emission rate is and what's the emission rate of the marginal generator displaced by that generator. So for example, if your own emission rate is zero, but you are displacing a coal unit with the, say, with the emission rate of 1 ton per megawatt hour, then you actually achieving negative 1 ton per megawatt hour of displacement efficiency. That's why building renewable actually contributes to carbon displacement. If you are displacing instead the combined cycle unit with only 0.4 ton per megawatt hour, then the same renewable unit is 2.5 times less efficient in carbon displacement than the one that displaces coal. And that actually tells you, it doesn't make really sense to put your generation, to continue building renewable in the area which is already dominated with renewables, when at the same time you can spend your money multiple times more efficiently, place it in a place where you displace dirty coal or inefficient oil units.
Makes sense. And so it's also interesting that there's very little storage, both short and long duration. And I'm also trying to remember your presentation from yesterday on long duration storage. So could you comment on like that if nuclear was not possible to be built, would there be more storage? And also Maryland has a 3 gigawatt storage goal by 2033, which I'm not sure is how it is being reflected in this.
Well, I mean, you could build, if you could build storage and have the technology that would really accommodate that. I mean, in yesterday's presentation, we're looking at sort of a hydro system. Unfortunately, we were not, could not consider the sort of similar technology available in Maryland. So, and all the storage we looked at was like a battery storage. We would not be sufficient to address all the congestion issues related to, say, building more offshore wind in Delmarva. So that's why we had to turn into nuclear as the source of zero emission generation.
I appreciate it, Alex. Thanks.
Thank you. Thank you, Rajat.
Do we have any more questions in the room?
Russell Polaris. Just on the last one, I'd remind folks that nuclear does not necessarily reduce the need for storage. In fact, the pump storage plants that we have in this country are largely built to balance nuclear. So they actually required storage to be built, not the other way around. So in your examples, one of the things is always coming up with a simple story that you can convey. And I was struck by the numbers that you had for marginal emissions in Maryland, which were average numbers over time, right? And to the point of, so you want to build your, you get bigger impact by building your renewables in the high marginal emission zones versus the non-marginal. But it is hiding the dynamics of the system because, well, if you build storage, I mean, if you build solar versus wind, it could have a very different effect on marginal emissions because of what you're seeing on the more granular time frames. And have you looked at getting the numbers to show, okay, well, maybe in Delmarva you don't want to build wind, but you may want to build solar or vice versa because of that time effect?
No, we certainly looked at that, and as you know, we looked at the marginal emission rate with the hourly resolution. So we understand that the dynamic is changing and what happens in, say, one set of hours and another. But the problem is not just that, but also transmission capability, because the transmission network in Delmarva is very weak, and I mean, it is a time issue, but it's also kind of, regardless of the time, there is a limitation. And in addition, there is overall, there's another aspect. I'm not sure how it affected. We need to take a look by Delmarva generation, but there is a general BC-PEPCA interface that is limiting import into the BGNA and PEPCA area. And there is so much you can push until you have to upgrade the transmission capability, which we simply did not look at in this study.
Any more questions in the room? Do we have anything online? All right, Aleksandr, thank you very much. All right, I think that concludes this session in the hearing room 1. The session in the commission meeting room is still running for a couple more minutes, and there will be the last session of the conference there at 12:30 today. Thank you all for coming, and thank you for your presentations.